All right, welcome everyone. Almost the last day of class. Thank you all so much for being here, all the students. We have a lot of external guests here with us today, and also quite a few people online as we're live streaming this event. So thank you all, really excited to celebrate this day with you. All right, so we have a lot of great presentations to go through today. Here's an overview of the agenda. So starting now, this is the welcome. And then we're gonna split our 10 teams up into 2 groups of 5. And each team is gonna have about 8 minutes to present, and that includes the Q&A period. Then we're gonna have a 10-minute intermission. And we have some wonderful food and beverages right outside here, so you all can take a quick break, get some snacks. And then we'll continue on, and then we'll close things off. And so here's the order of the teams that we're going to present today. So before we get into the presentation, I wanted to just give you all an overview of Wake Forest Engineering. I know many of you are very familiar with their program, but also just for people who are not as familiar and people online. So this is our 5th graduating class, which is really exciting. Engineering is pretty new. We're the newest department on campus, and our program is very unique, right? Wake Forest is a liberal arts institution focused on undergraduate education, and so we have a really unique curriculum, really unique program that's grounded in the Wake Forest liberal arts tradition. So we have a very flexible and very innovative curriculum that our students have gone through, and we also are AVID accredited. So this is a national accreditation agency, and so we have gone through, met all of those requirements, and we still, meet all the same requirements as the big, huge engineering schools that get completed. Pro Humanitate, hopefully most of you have heard that motto before. It's the Wake Forest motto, and it really resonates with all of our students and our faculty. As we were building out this program, this was really central to how we thought about our curriculum, how we thought about the projects that our students do throughout their 10 years. You might also be familiar with this idea of a whole engineer. And in addition to those very fun and interesting projects that we do throughout, we also talk about what we call character virtues. Right? Engineering education is not just about the technical skills, but also a lot of the virtues and having students reflect on how their decisions have impact on society. So, for instance, in Capstone, you all know that we spend a lot of time talking about teamwork, right? Taking time to reflect on how we're working with each other, practicing, giving each other feedback, right? And making improvements along the way. And then our department, we have values that we bring up all the time. So they're integrity, empowerment, inclusion, growth, compassion, and joy. So joy, it's really important that we have fun, right? Engineering is tough. We have high expectations of our students, but we try to have fun. So speaking of joy, I'm really excited to announce that one of our design teams that you're going to hear from today, they placed second in a really big competition, the electric boat competition, the electric boat team. So we're super proud of them. So hand applause, guys. So you'll hear more from them, but the teams they're competing against had way bigger budgets, way bigger support. So amazing that they took this place. And big shout out to Dr. Crow and Mr. Greg Muller, because y'all really, they put in a lot of effort to get them there too. So all to say, like the faculty, the staff, they're always there supporting these teams. Okay, a bit of background about the engineering senior capstone design. So engineering capstone is a culminating design experience where you're applying everything that you've learned from previous courses. So while you'll see Dr. Crow and I up here because you're the instructors for capstone, all of the faculty have played a part in these projects. So it really is a team effort. The students are working on real world problems. So we source projects from local companies, from local government, from nonprofits. So they are working on projects where there has been a real need defined by real stakeholders. We also assemble expert technical panels for each team And so some of that are our own faculty, some of that is a project sponsor. Often students will find technical experts to bring in on their projects. And often these experts, have different stakeholder perspectives on who's going to be benefiting from the deliverables from these projects. The students have to integrate real standards and constraints. And then they really consider the broader social, economic, and environmental impacts of their projects, and that is closely integrated into their design. And so there's there's 4 phases of the design process that takes place over 2 semesters. So the students have been working on these projects over a full year. So it started off in the fall semester in the discovery design phase, where they're exploring their topics, thinking about stakeholders and impacts, and then going into conceptual design, so looking at a broad range of alternative solutions to select which one would be the best for their needs. And then in the spring semester is when they really get into the hands-on work, the prototyping, building, and then the detailed design. And some of these projects were really open-ended at the start of the fall semester, right? And some of them were even student ideas, kind of out that you'll hear from today that were just, you don't really have any idea of the best solution. And some of them were more scope, some of them are continuation projects. So when you see the presentations today, you'll see a range of kind of scope and how far they got. But that is by design. There's a wide range of projects that we work on. So with that, because we are on a tight schedule, I don't want to talk too much. I really want to give this space to the students. So I'm so proud of it. It's been so fun to work with you all. And so again, this is the overview. And so I'm going to ask Pharmacure, our first brave team, to come up and kick off the symposium, to come up. And then I'll explain the microphones for everyone. So we have a microphone here, and then we have a microphone and clicker here that I'm about to turn on. And then there's a clicker here, so you guys can spread out and you don't have to pass everything back and forth.
I don't think I want a sticker. Wait, Teresa, are you just gonna click it, or do you want to be around? All right, give another one.
I want to look really confident.
Yeah.
Yes, we can do it. Okay, there we go. It works. No.
I think it should be.
No, wait, I'm not talking to a mic. I'm not talking. Do we need to use the mic or not?
Hi, everyone. We are Pharmacure, and we're going to tell you about our device, the PharmaPal. This is our team.
I'm John.
I'm Mira. I'm Grace.
I'm Teresa.
I'm Elena. So the problem is that only about 50% of U.S. patients actually adhere to their medication routines accurately, and then this further decreases with an increase in age, an increase on dependence on caregivers, an increase in regimen complexity, as well as with low health literacy. And then this results in consequences such as about $300 billion in annual preventable healthcare costs, about 67% of medication-related hospitalizations, and about 120,000 deaths, preventable deaths annually per year.
So our market need, our goal is obviously to then promote independence, reduce errors of medication taking, and also ease burden on the busy caregivers. So the primary users of this device would be elderly and cognitively impaired individuals, busy caregivers, as well as healthcare systems and also home care services.
So we've sorted the existing solutions into 3 separate categories. The first is pill containers. These are pill calendars. These can range anywhere from $200 to $200, but essentially the user has to manually put each dosage into individual compartments, which I'm sure many of you guys know is very tedious. The next, we have prepackaged prescriptions. So if you have a prescription with Amazon Pharmacy, you can get a pill pack for free with your dosages in them. These are made out of plastic, which is bad for the environment. And if you have to change your dosage, you have to order a fully new prescription, which can be really wasteful. And then there's also fully automatic systems like the Hero, which require the use of an app and Wi-Fi. A lot of users complain about issues with the setup and the accessibility of this. Also about the fact that this is a subscription service at $45 a month.
Noticing the gap in the field after the team's background research, we decided to create a device that combines the good parts of each solution and also tackling the more negative aspects of each. And through this, we were able to create our device, the PharmaPal. And this is the world's first standalone and autonomous medication dispenser. And this is great for users because there's no smartphone needed, no Bluetooth, or any manual pill sorting required. So it drastically reduces the burden on both caregivers and any medication takers. So by this, we're able to eliminate the need to pre-sort doses and make it more simple for everyday use.
So there's a few key components that we incorporate into our project. The first is where do the pills go? Into the pill containers. You slide up to a 90-day supply in there. And then to choose which pill, we have a rotational motor that spins the pill holder around in order to pick up the pill. And then in order to pick up the pill, we have a vacuum pump. We decided it was the best way. There's not much friction with it, and it allows like ease of use. So the vacuum will turn on, and then we have a linear actuator which will pull it up and down to pick up the pill. And then to test to make sure that we have the pill, we'll use a pressure sensor. So I'll kind of go over how it works. You're going to input your dosage and schedule the set time. Then you'll load the pills into the pill containers up to a 90-day supply. The device is then, when it at the right time, is going to spin the rotational motor to the right pill. And then the linear actuator is going to go down to the bottom of the pill holder. Then it's going to pick up the pill with the vacuum. And then the pressure sensor will check the pressure. If the pressure is decreased, so it means the vacuum has made a seal, it will continue up. If not, it will try again. And then it will rotate the linear actuator or the rotational motor again and drop the pill. And it repeats as much as needed.
Here's a video of it working, set up, so it's kind of slow. So you can see here, it goes up and then it checks again, so it goes down. So it didn't make contact, but now it did, so it'll go completely up. And then the yellow is the drop point, or normally blue. So while it seems pretty technical behind the scenes, it's very simple for a user to be able to use in their daily routine. Firstly, you would input your different dosage and dispensing schedule for each medication type. And like John said, there's four different types of medication you're able to put in, and up to a 90-day supply of each. You load their pills into their designated containers. Then we wait for the dispensing time in which the machine will begin its process, rotate around, pick up a pill, and finally the user will collect it from the retrieval cup and take their medication. So very simple for anyone with any cognitive disabilities or increased age.
So we've been looking through our testing phase at 3 specific factors. We've been looking at dispensing accuracy, dosage accuracy, and timing accuracy. Dispensing accuracy relates to the successful pickup and dispensing of a pill into the retrieval cup for the user. The dosage accuracy relates to the correct amount of each pill type being dispensed, and then timing accuracy relates to confirming that the pills are dispensed at the scheduled times as inputted by the user. And we have conducted exactly 300 tests with a 90% success rate, and within just the last 268 tests, we have a 100% success rate. So we are confident in saying that our device is 99% successful over a 90% confidence interval.
And then going forward, we would want to add a filling function to help users fill the pills easily, as well as a code to count and verify remaining pills in the container. And with that, maybe a weight sensor to weigh the total 90 supply, and then as pills are dispensed, recalculate the weight to again check for remaining pills. We'd also want to focus more on testing specific cases. So when there's like a few pills left in the container, also we'd want to make it battery powered in case power goes out. And then we would also want to have it support more than 4 medication types. And then lastly, one thing we would want to change is instead of using Arduino, especially for our interface, we'd want to use Raspberry Pi because the user interface with Arduino caused us a lot of problems. Thank you for listening, and we'd be happy to take any questions now. We're not. So,
Why do you want to Raspberry Pi?
well, the Arduino Giga is the board we used, and it's like compatible with the display shield, which attaches onto the back. And all throughout, like creating the interface to like incorporating it with the motors, it has been a nightmare. I don't know, John can also touch more on it, but it's just been really hard to integrate. And even for user interface, Raspberry Pi is much easier to use. The Arduino coding was very difficult.
Yeah, there's like no easy setup with it. Like every line, every letter, you have to if you touch the screen to say the exact coordinate position of where it would be. It's not really user friendly. Also, doesn't have much RAM, so like you're running into issues with like having string functions in the Arduino. At a certain point, with all the things you're putting into it, like 900 lines, it would crash. So you had to switch it all to char, and it was just like a pain to do.
If you like touch it too quickly, like it'll just reset. So it's just like not compatible. Yeah. I don't want to hold it. Yeah.
Yeah, we tested. Oh, he wanted us to answer like the range or the size of the pill that we've been looking at with testing our device. Oh, and geometry. So we looked at 3 different pill types. We have like a capsule shape, and then we have a gel pill, and then we have also just like a regular circular pill, kind of like what you see with ibuprofen. Our device has been successful for all of those pill types. We've been mainly looking at the gel pill because that's the pill that gave us the most issues with when picking up, and that's what our testing data was based on. But our device has been successful with all 3 shapes and sizes of those 3 pill types.
And the nice thing about our vacuum is that it's so strong that it can pull any shape towards it. So we might have had some issues at first, but once we got the right vacuum down, we found that pretty much any shape could be lifted up.
Thank you.
Yeah, you don't. It's up to you. Another mic.
Yeah, right?
Okay.
Yeah.
You can give it a start. Very nice.
We should all just
Yeah. Okay. So no mic.
Refresh the page just to make sure it's not like something with the
All right. Next up, we have the PD eval team.
Do we need the mic?
You don't need the mic. Yeah. Here, there's not.
nice but people. All right.
Okay. Tiny hearts, big innovation. Welcome to the PD eval. 1 in every 100 babies are born with congenital heart disease. That amounts to about 40,000 per year. What is congenital heart disease? That encompasses any birth defects or performance enhancers where as a child they grow up and it doesn't meet the requirements you might have when you're running or walking around. So what's the result? If it's severe enough, you might need to have repeated open heart surgeries. Of course, that's going to be risky. But after that, you also need lifelong reliance on medication. Now, this can amount to about $250,000 in medical expenses. Now, you might think with the advancements in modern medicine, how is there no solution yet? But I'll leave it to my teammates to talk about what the gap in the industry is and where the PD valve comes in.
So why the PD valve? Currently, there's no device that exists for catheter-based aortic valve delivery in infants. There's only 2 options. The first one is open heart surgery, which is costly and invasive. The second one is constant monitoring of conditions during childhood, which poses immense risk. What do we need? We need a safer, less invasive solution.
With this problem in mind, we began designing the PD valve. We knew that it needed to compete with the best, which is why we benchmarked against standards of care currently on the market, such as the Zephyr Stem and Edwards Sapien 3 Ultra. However, there's a crucial problem. These devices cannot be scaled down to the anatomy and physiology of that of an infant, which is where our product differs. We looked into materials such as cobalt chromium, as well as nitinol for the frame, to leverage existing mechanical properties within the space, as well as Gore-Tex/EPTFE for the skirt, because of its biocompatibility as well as reduced risk of immunogenicity. We even considered coating the metal frame with an anticoagulant drug such as warfarin. To ensure that we weren't designing this product within a vacuum, we consulted an array of pediatric cardiologists as well as cardiothoracic surgeons to gain useful insights into what the main obstacles are within the space of pediatric heart valve care. We identified that for our patient demographic, there aren't many minimally invasive interventional procedures available, and many of these patients have to undergo high-frequency interventions over their lifespan, even becoming overly reliant on long-term anticoagulant use. With this newfound insight, we took a step back and analyzed under a clinical as well as engineering lens what the most important features were that we were trying to accomplish within our device in order to move in the right direction and in accordance with our time as well as resource constraints.
In the past year, there was a lot of trial and error. We began by creating a CAD model of the valve However, this came with a lot of limitations. The valve would only fit the scale that we needed at 10x the size of the scale. You see in this picture right here that that's actually the size of the whale's heart. It's 10 centimeters. Anything we scale down to what we needed, just kind of falling down itself in this work. We took our gear to SolidWorks. This is a software that we use to create the valve. And you can see our early iterations right here don't exactly match what we were looking for. They don't look exactly like what you've shown on. So this brings us to our final prototype. This is our SolidWorks model. It's made out of PTFE, which is a plastic fabric. It's incredibly durable and non-reusable. And it's surrounded by a nitinol and titanium cage. As you can see, that there are two separate parts here, and then we can combine them together. And this model can be used for computational fluid dynamics. So what does this look like off the screen? We were able to actually create some prototypes. These are all to scale and known as physical fitness things. But you can see that we have a cobalt chromium frame and an early iteration layer. It was a bit too stiff and a bit too wide for what we were looking for, so we switched to nitinol. It's a lot more flexible and durable, and can actually adapt to a little bit of growth in the child's heart. Additionally, a child's heart has less blood pressure, so it would be good for that. You can see that each TPF research, all three of them, and the V-sets have it in the leader iteration. So the final iteration is up there. Again, the 3-liter skirt does about 9 millimeters across, and the nitinol. So with just scaling down the valve, that was not all that we were looking at. We were also looking at deployment methods. So as you can see in these two videos, this kind of shows that the valve would actually be deployed via the femoral artery of the pediatric patient. And through that, we needed to look at what occupancy rate the actual valve could fit in within the femoral artery. So as you can see here on the right, there is some space between the catheter and the actual artery because you have to occupy only up to 33% of that artery. And so we used a 4-branch catheter, and as you can see here on the left, this is kind of how the valve would actually look stripped down and then expanded in the pediatric patient. So not only did we create physical prototypes, but we also really needed to focus on a computational model to show that our valve could withstand the pressure and velocity that is seen in blood pressure. So when this is just an example here of at max blood pressure, what the velocity of the blood going through the valve would look like. This kind of shows the pressure and velocity of that and what the difference in gradient is between flowing through the valve, and this was created based off of values found in research with this size valve or also through calculations.
We're very proud of everything we've been able to accomplish throughout the year, and we've gotten nothing but great feedback from all our stakeholders. We've been able to create a modeled valve, simulated performance, as well as prototype design. These 3 big accomplishments have allowed us to bring a drug-free future as well as transcatheter access. Let's save lives together. Invest in a healthier tomorrow,
one tiny heart at a time.
So initially we were looking at infants like under 1 year old, but that proved to be a little bit too challenging size-wise, so we moved to the 1 to 3 year old range. Yeah, so our goal was to really just focus on taking away 1 reintervention surgery because when they are growing, the valve size of a pediatric patient is exponentially growing with the child. So just to be able to kind of address one of those reintervention surgeries and maybe take away some of the other parts of that with like anticoagulant medication use and the open heart surgery and cost of that. So our goal was to create a catheter-based solution that would reduce the loss of life.
Excellent job of timing so far. Next up, we have the sustainable shredders. Oh, whoa, weird. How'd that happen? Okay, weird. All right, sorry, y'all. I guess we were testing these. We overplanned and then. Thank you for letting me know. Do y'all want two different?
Yeah. Good. Okay. Hi, everyone. We are the Sustainable Shredders, and for our project, we built a medical waste plastic grinder to be implemented in Atrium Health's new STEM lab in Charlotte, North Carolina.
So you ever wonder what happens to use medical plastic waste, like these pill bottle containers, these pill bottles or these syringes? So a lot of these plastics that present no biohazard risk still end up in incineration plants like these. So our thinking was how can we use this plastic for something better? So we designed a medical waste plastic grinder that can help be used to upcycle these plastics and teach students about upcycling and engineering in a creative manner.
So let's take a step back and think about the broader impact that healthcare has on the environment. The healthcare industry produces 10% of the greenhouse gas emissions in the United States, which is a huge amount for a sector that's meant to heal people. It produces tons of plastic waste daily, and 91% of this plastic is not recycled or upcycled in any way. So clearly, there's a need for an innovative, scalable solution to take this waste and repurpose it.
Yeah, so our mission statement, basically, not only do we want to create a machine, but also be interactive with other students and educate them about the positive impacts of sustainability and upcycling, and even educate them on real-world power and energy concepts through our plastic grinder. Not only that, but we also try to inspire future engineers and also lead the charge in Charlotte, North Carolina regarding plastic medical waste crisis.
So looking more closely at some of these impacts, first the social impacts, like Erin was saying, we're going to help educate students on sustainability and engage the local community in upcycling efforts. And then we will also help support Atrium Health STEM initiative in their new hospital.
And then economically, economically, this could help hospitals possibly save some money. So instead of paying someone to get rid of the plastic, they could possibly reuse it. And then scaling up this project, that could help add the saving up. So both in disposable costs and then in the value of what the plastic becomes.
Looking more at these environmental impacts, we can help reduce our plastic waste through upcycling. We can also use our bike-powered system to not always use that motor and create fossil fuel emissions that way. And we can also promote a circular economy in healthcare, which Kristen will talk a little bit more about. And then looking at our system as a whole, we can break it down into three main parts. So the first part is our bike system over here, and then we've got our motor system. And then here in the middle, we've got our actual grinder with our collection bin and our chute. So our solution is a closed loop solution that connects healthcare, sustainability, and engineering. So it all starts at Atrium Health, where by treating patients, they throw away tons of single-use plastic devices every day. This plastic gets collected and given to our project. The students in the exhibit can input the plastic waste through the
shoe at the top. The enclosed acrylic shoe promotes sustainability and accessibility and education. The plastic waste falls onto the grinder blades, which gets power from either a bike or a motor, and then turns into plastic flakes. And these flakes will be used for upcycling, so either in 3D printing or injection molding, any way to make other medical devices that will ultimately go back to Atrium Health, closing the loop and reducing waste.
So comparing our two sources of power, we have a motor and gearbox and a bike and chain. The motor and gearbox represent more of an industrial solution that can be upscaled to really create a widespread difference in the plastic issue. And this is a really high power solution, taking 230 volts from the wall. But this also represents kind of the downside, where this is not something that everyone can access. It's also really expensive and just not really feasible for the everyday person. On the other hand, the bike and chain is kind of more of an approachable solution that anyone can reasonably do with some money and some engineering skills. And this is allowing us to really educate people on how much power is going to be able to be needed to grind up plastics. And the downside of this is that human power is less powerful than the wall power. So when we reduce the speed down to get the necessary torque to break up plastic, we're not going to be at such a high speed, meaning we're not going to have a very high output. So this is just not really going to create much plastic. So how it works is we have two parallel shafts that rotate in opposite one another, and there's blades all on these shafts. Like I said, it's very high torque, so it's powering through at a low speed to break up any plastics that are put in. And so here you can see the motor and the gearbox. This is the gearbox is the silver element on the right, where the motor is the blue one on the left. The motor spins at a very high speed but low force, and the gearbox just reduces that speed to get up our force up to the necessary amount. And this is really expensive, but it's high power. Yeah, so now looking at our bike system, so we had to make a few modifications before we could apply it to our system. We wanted to lock the rear gears to prevent the user from interfering with any added parts that we had. We added a second chain to the back cassette so that we could take the output from the human and put it into our system. And we also removed some unnecessary components like the kickstand and rear brake just to declutter our system. So now once we get the power out off of the bike, we have a custom-made gearbox. We use chains, gears, and bearings to increase the torque and decrease the speed. And like Jared was saying, to get that similar torque output used to grind plastics, we need to reduce it more, and we have a lower speed.
So yeah, so what's coming up next is that this project will be a continuing Capstone project for next year. So there will be a need to see some improvements, such as refining the grinding system, making it more aesthetically pleasing, and then adding to the application material. So then after that, as Greg said in the beginning, this will be going to Atrium Health's brand new STEM education center, where students from kindergarten through 12th grade will be able to use it as a part of sustainability programming, and hopefully help us create a cleaner future. Thank you.
Seems like what you actually built.
Yeah, it could definitely be applied to a big variety of industries. We're focusing on the medical industry just because this project was proposed by Atrium Health and had the partnership with them. So they really wanted to focus on their sustainability and STEM education. And like we said in the beginning, plastic waste is a huge issue in the medical industry. So that was why our project is focused on medical plastics. But yeah, it can, have a big variety of applications and could be used in tons of industries that want to cut back on their plastic waste.
Next up, we have hydro and power.
engineering. We're Hydro and Power. Thank you for coming to the symposium, and thank you for your attention during our presentation. I'd like to start us off with a question. Can anyone here tell me what they think the CDC recommends should be someone's daily water consumption in liters? 5? Can be more than that. Good guess. So hands in the back. 7? Still more than that. Anybody? In the corner there? You got a guess? 10? Oh, we're gonna double that. It's actually 20 liters per day. And so, for context, that's about 80 cups of coffee.
So unfortunately, not everybody has access to that much water in their day-to-day lives. For a lot of people around the world, they have to travel many miles just to get access to clean water. For our place, where we've been looking in the Rwenzori Mountains in Uganda, about 43% of people live further than a kilometer away from freshwater access. And of that 57% of people, 60% don't have access to potable, clean drinking water. So, to address this, our main stakeholder, Dr. Dickinson, designed a gravity flow scheme, utilizing the power of gravity to deliver fresh water from higher elevations down to these local communities in the Rwenzori Mountains. So how it works is there's a river up in the mountains. This goes through a slow sand filter where all the contaminants are filtered out, where it is then potable. That is then stored in a reservoir where it can then be pulled using gravity through pipes. However, when you go through these pipes, a lot of pressure is built up. So you have to release that pressure back to atmospheric pressure in these things called break pressure tanks, seen there. From there, it can then be delivered at a safe pressure and a constant flow rate to local taps, delivering fresh water to these local communities. Now, having addressed the issue of water, he realized there was another issue, electricity. In rural Uganda, roughly 57.6% of people don't have access to electricity. And in these really remote locations, that number is a lot higher. So what are we going to do about that?
So given these twin issues of water access and electricity access, we derived this set of system requirements that we want our solution to address. So the first one and our biggest priority is actually drinking water. So first, we want to maintain the pressure and flow rate of at the access taps. We also want to avoid contaminating water because it is drinking water. And finally, we want our system to be resilient enough to last 20-year lifetime of the gravity flow scheme. The next thing we want to do is obviously provide electricity. So we want to be able to do this safely, and we want it to do it in a way that is accessible to the community so that they can actually access this as close to where the community lives. And finally, we want it to be temporarily accessible as well, so that electricity can be accessed even when water is not flowing through the system. So the last thing is also on that theme of accessibility. We want our system to be modular, meaning it can be implemented anywhere in the gravity flow scheme. We want our system to be the parts of our system to be able to be purchased in Uganda, and we want them to be able to be purchased for a reasonable price so our community can afford the electricity.
Right. So what do we plan to do about this? That's why our team has designed a hydroelectric generator designed to work with the break pressure systems and tanks in the gravity flow scheme, comprised of a Capstone turbine and permanent magnet alternating generator that will take all the pressure basically and turn that into energy we can use. So if you can recall, this is the visual map of it. This is the service area where all the water's being out from, and all these yellow squares you see here are the break pressure tanks. So our team has picked out a square here in the middle where we found we could get the most available power that is near the most amount of residents in the area, so it's more easily accessible to them.
So we've done the calculations, and our system is projected to reach an instantaneous power of 460 watts, and this is about 3 kilowatt hours in a day, and at about 60% efficiency. And so in context, this would power in one day about 198 phones or 49 laptops. So how do we test our system? So to simulate the real world conditions of the Rwenzori mountain water flow, we used a powerful jet pump, that little V symbol, and it takes water from a simulated water reservoir, that blue tank, and then shoots it through a PVC pipe, PVC being a material that doesn't impede the water quality of our system, into a Capstone turbine, that gray image on the top. You'll see a real picture of it soon. But the Pelton turbine spins and water falls through the bottom, then dropping back to atmospheric pressure, flowing back through another PVC pipe into the blue tank, creating a full cycle, a closed system. And then on the electrical side, as the Pelton turbine spins, it's attached on the back to a permanent magnet alternator. And this creates electricity while it spins, going through a charge controller, which effectively controls the current coming in, making sure the batteries don't overflow on current, and then through a battery management system into 4 lithium iron phosphate batteries in series, totaling to 12.8 volts, into an inverter, and then finally at our end user where we can charge. There we go.
So this is more of a close-up of the turbine. As you can see, it's running pretty fast right there, so you have to get a good visual of it. And then right on the backside, simultaneously, the generator is also working with it to produce that power.
So having tested our system, the first thing we noticed is that our pump actually was not able to match the conditions we were expecting in Uganda. And so instead of giving us 55 meters of head at 1.5 liters per second of flow rate, we instead got 30 meters of head at 0.6 liters per second. So this means instead of having access to 780 watts, our turbine instead only sees 180 watts. And so we're still able to produce power about 40 watts at 22% efficiency, but we were expecting to get 460 watts at 58.9% efficiency. However, we are actually not dissuaded by these results because of the way that our alternator works. So the alternator is designed to work at 1300 RPM, and it's only given 500 RPM. So alternators have higher efficiencies at the speeds they're rated for, so 1300 in this case, and they'll have a much lower efficiency at a lower speed like the one that we gave it. So given that we're not able to verify our expected power, we were able to demonstrate proof of concept, and we were able to show that we could produce, store, and deliver electricity safely and reliably.
So where do we go from here? First thing we want to do is be able to actually simulate full conditions of the system in Uganda. So that means getting a stronger pump, hooking up to our system, and actually getting that 50 plus meters of head and the 1.5 liters per second flow rate. We also are thinking there are ways that we can adjust the nozzle diameter, maybe to give us a better flow or a closer flow to our actual system. And then, yeah, we want to prepare future teams, hopefully, to continue this project to get it closer for potential actually implementation in Uganda. Thank you all, and let's make every drop count.
We're going to go to the next team and stand back. I just want to ask some questions for the transition. You're more than welcome to. We want to make sure everyone's good job, guys. Next up, we have safety bike. Which one of the microphones is working? They are working. This one just turn on. And then flush it off and get feedback. So if you want to turn it on. Oh, is it on? I don't think it.
Hello.
Yep, it's on.
Hello. I don't think we need one.
Okay.
We're good.
Cool. Good morning, everyone. I'm Blake. I'm Charlie. I'm Johnny.
I'm Madeline.
I'm Ernsley. And we're the Safety Bike Group. We're really excited to show you what we've been working on this semester. So the scope of our project was enormous. We were basically essentially told, make e-bikes safer. And, there's a lot of options and ways you can go with this. So it was really important for us to develop a really defined problem statement. Ours reads, the rapid growth of e-bike popularity has caused a sharp increase in e-bike related accidents, injuries, and deaths. And this is why we decided to focus on visibility. But how do we know this? Let's understand the problem. What makes an e-bike dangerous? It's heavier and faster than your traditional bike, but it's also used as a vehicle. Many people will take it to work, they'll take it to class, stuff like that. And some other important statistics to note. In 2023, 8.2 million people in the USA rode an e-bike, but there's also been a 49 times increase in e-bike cyclists with head trauma in the last 5 years. Obviously, this is unacceptable, and thus an adaptive brake light was born. The first iteration the team designed was a wraparound brake light that was supposed to fit on the back cargo rack of our e-bike.
This design, although it looked great, it was too clunky and it didn't really work too well. We then used a 3D scanner to scan and accurately measure the back cargo rack, which allowed us to get this model, which perfectly fit the bike rack, but upon receiving feedback from our stakeholders, we ultimately decided it was too large. We then downsized to this next iteration. It's smaller, it's swappable, and it's more simplified. The issue with this one, though, was it was not optimized for our internal electrical components. Finally, we then moved to the final iteration, which has a sleek design, more optimized space, better lighting angles, and it's made entirely out of glass fiber ABS, which is better for weathering conditions.
So while we were figuring out the shell, we were also figuring out what light we were going to do because it's a brake light. So we ended up deciding on 4 different modes. So we have standard setting, slow braking, extreme braking, and turn signal. On here, you can see what each one's going to be flashing. But basically, the standard setting is you're just riding along, you're not slowing down, you're just having fun. Slow braking, it's kind of self-explanatory. You're slightly braking. Extreme braking, Bambi is in front of you. We don't want to hit Bambi. So you're extremely braking. And then turn signal, kind of self-explanatory as well, but we have a Bluetooth module that's connected to the handlebars where you're able to press the button that indicates the direction you're turning. And so once we figured out the lights and we had the shell, we had to figure out what we were going to cover the lights with. So our lens cap. So with that, we 3D printed using a red translucent PETG filament, which is stronger than PLA. The design of it is supposed to perfectly fit the outer casing of our shell, while also providing great light diffusion.
So now that we understand what we're working with, let's talk about the testing and engineering behind our product.
So let's get into really the heart and soul of the adaptive brake light, the electrical system. This system is built on an Arduino Pro Mini, which is really the brain of this entire operation. We chose the Pro Mini because it's a compact size, it is very capable for what we needed it to do, and it has good memory capacity for the programs we would be uploading. This interfaces with a GY521 accelerometer that captures acceleration data from the bike as the rider is going along and braking at different intensities. With this information, the Arduino makes a decision to activate one of the 3 different braking settings. But how are we going to decide, how does the Arduino decide when to activate which setting? For that, we had to find some braking thresholds. For these, to identify these thresholds, we did some testing and we created a test module that we placed on the back of the bike, and we ran several tests. A few different riders, we had different stopping distances and different starting speeds. And from these tests, we developed our 3 braking thresholds. As you can see here, we had some data. The data was actually quite good from what we pulled off of the SD card. And we were able to see pretty distinct differences between our just riding along steady, kind of, no braking, our slow braking, which was about, we got a lower threshold for that, and then the extreme braking, which we see up here, had some higher numbers and pretty consistent readouts among different tests, and we were able to define 3 distinct braking thresholds.
So if you haven't figured it out, our things about light, we need to be able to test that light. So by testing that light, we use a light meter, which measures in lux. We needed that in lumens. So we figured out a distance, and you could visually see our light was way too bright, but we also were able to quantify that it was way too bright. And with this information, we were able to adjust it in the code and decrease it to be these numbers above.
And so the last component added to our system is the turn signal module. And so it's using the HC05, the Bluetooth component. It can be configured to be either a transmitter or a receiver. And so the transmitter is in our prototype, as you can see pictured on the handlebars, is powered by 4 AAA batteries at 6 volts. And so the way it works, you just either press either the left or the right button, and it overrides the current lighting system on the adaptive brake light. And we've done some testing on the reliability and accuracy, and the distance between the handlebar and the adaptive brake light on the e-bike.
So now that we understand exactly what we're working with, let's see how it works. Johnny's going to quickly explain what you're about to see in the video.
So we have a video of our prototype. Unfortunately, this morning we were having some issues with it, so we could not bring the working prototype in here. In the video, you will see we have our 3 different braking modes. The standard, we have slow braking, and then, so we have our standard setting. Tilted up, it's the slow braking, and then all the way up to that extreme flashing.
Right here, we're using gravitational acceleration to trigger the accelerometer instead of just like shaking it really hard to get the different modes. But those are the 3 different modes we have. That is our prototype, which we will have working obviously for Monday. Yeah, that's it, and we'll take any questions.
Thank you.
One quick question before we go to intermission.
Yeah, so the housing itself is powered by an 11-volt LiPo battery. This interfaces directly with the Arduino. It can take up to 12 volts of raw power. It also goes directly to, kind of hard to see in there, it's a bit of a mess in the back of the wiring. So this kind of goes directly to all the components. And luckily, this was able to power the LED strips without the use of a boost converter, which we were initially thinking we would have to use.
Thank you very much.
So let's take like a 10-minute break. There's 2 right outside, so come back right around 12 or yeah,
'em. All right, welcome back, everybody. We're going to go ahead and get started with the second half of our symposium with Ocean's Motion. Take it away, y'all.
Quick shout out to Jackson's birthday. Anyway, ladies and gentlemen, thank you for joining us on this fine afternoon. We are Ocean's Motion, and we are very excited to present to you a revolutionary technology that is able to harness energy from the movement of waves. I am Jack Wynett.
I'm Jack Griffiths.
I'm Walker Reynolds. I'm Cristóbal.
Mason.
Jackson.
And to get started, we're going to give you a little bit of background context on why we chose this project and what Ocean's Motion means to us.
So first and foremost, we want to thank Wake Forest Engineering for approving this project. This has been, I can speak for all of us, an incredible project, a very personal project to work on. So let's get into it. This all started in the Philippines. This is where I'm from. My mother and I, when we were little, we used to go on medical missions around the Philippines, and we stumbled upon this cluster of islands. This is on the eastern side of the Philippines. Just to give you a little bit of background on why we chose these islands, they are inhabited by about 1,000 people. Each one of these islands has its own elementary school, and the economy around these islands, because they're so isolated, is mainly fish. So what's the problem? Because these islands are isolated, they have no access to a national grid. This means that for any amount of electricity, they are reliant on government-owned diesel generators, which are incredibly unreliable, and they cost these communities $1 a day per household, which, given the income of each one of these communities, is a lot of their daily income. Another thing we've found important for you guys to know is that a lot of these communities have now become cashless, meaning they use systems called GCash, similar to Venmo, meaning that they require their phones. Because of the lack of electricity and the reliance on these diesel generators, not having a constant supply of electricity can be detrimental for them being able to communicate with outside islands. Another very important factor is that a lot of feedback that we got when communicating with these communities was the fact that children can't study at night. Once the sun goes down and you can't afford that $1 a day for that diesel generator, you have to go to bed. You can't. It's very hard to function. So Our idea of being able to supply these communities with some reliable source of electricity was very important to us.
And that brings us to our mission statement, which is to introduce a cost-effective and renewable energy source to generate usable electricity from the power of the ocean. So in other words, we want to create a system that will convert the natural kinetic energy from ocean waves into mechanical energy, which will then spin an electric motor, turning into electricity. I also want to clarify that the goal of this project was not to reinvent their grid or anything like that. It was mostly meant to be a supplemental power supply for things like light bulbs or phones.
All right, now we're going to take you through our prototype process and just show you how we got to where we are now.
So from our mission, we set out to create a buoy that would harvest the energy of the ocean wave. Our first prototype we refer to as the aquatic line of prototypes, which was pendulum-based, which failed. The second was the avian line, which was rotor-based, designed similarly to the rotor of a mechanical watch. Then that failed, so we wanted to break it, defeated, and came back ready to dive back into research, which led us to our third prototype line, the amphibious line, which is a vertically leveraged buoy system. Yeah, so going back to the very beginning, like Mason mentioned, at the start, we were trying to harness the horizontal motion of the waves. So we were thinking like a ship rocking back and forth, our buoy would do the same. So that rocking back and forth that led us to create a weighted pendulum system. As Mason mentioned, it didn't meet the qualities that we were hoping for in design, so we pivoted. For our second line, the avian line. Those of you with mechanical watch, weight in the watch that we took inspiration from, that's where we got our inspiration from. So we were also trying to leverage the horizontal motion of the waves, seeing it as the watch would spin around. We would also get an axle to spin 360 degrees, still focusing on the horizontal motion of waves, but yet still unsuccessful, so we pivoted once.
So after our second design failure, we went through what we call our enlightenment phase, which is basically just another way of saying we pulled it together. So our first step was to really step back and reevaluate our goals. You know, we started this project very ambitiously. As Toby said, this is a first-year project, so no one had ever done this before. So we began thinking we were going to be testing in the water by like February, which was ridiculous. But we stepped back and changed our goals to just the mechanical system that you see in front of you. We'll leave the anchoring system, getting the energy from the buoy onto land, and the buoy shell all for later projects. But then we began to rethink what we were actually doing, the way we were designing our prototypes. We decided to go back to our research and change the target variable from the wave that we were actually going to leverage to make electricity. That's how we ended up with our reattack, which is our final model, a vertically leveraged buoy, which we're going to explain in a second.
And that brings us to the amphibious line, which manifested into our final model here, the axolotl model. And right here on the screen, this is our initial blueprint of our enlightenment phase. These are kind of the outline to what we envision the axolotl model would become. And we have a few key components that we knew we needed to leverage the height of the wave, rather from the lessons that we learned from the two other prototypes. So we knew we needed a pulsar coil to maintain tension on the rope as the buoy would rise with waves. We knew that we needed to conserve momentum, so we picked a very durable flywheel, which you can see right there. And we knew we needed a ratchet gear so that we could have our momentum going unidirectionally.
All right, now we're going to give you a little demonstration. One change that we did make from that one sketch is we centralized the pull start, just creating better balance. So Toby here is going to anchor on the ocean floor. As a wave comes, the buoy's going to rise, spinning everything and harvesting our energy with this light bulb. Hopefully all you guys could have seen that. And then, yeah, just to break down the main components. So like we said, we have this pull start, which spins our free spinning axle, which is held in place by our roller bearing and PLA housing. Attached to that axle is our ratchet gear, which spins the flywheel, which then charges up the motor. Thank you. So, any questions? Go ahead, Dr. Rowe, of course.
Given that you experience the design process, how would that change?
For anyone who didn't hear, you asked how did our enlightenment phase affect our process. I think what happened with our group initially was that we were very excited to start prototyping, and that's what we did right away. So without very specifically calculating each result, and it was fun. We'll admit we had a very good time that first semester, but it was a failure every time because there were things that we couldn't expect to happen because we weren't doing our full in-depth calculations. So being able to do that engineering mindset of actually doing a very in-depth research and calculating till the very end has led to the successful prototype. Thank you for that question.
All right, I think that's all we have time for. Thank you so much.
I don't know how we're standing.
All right, next up we have winchcraft. Welcome everyone. We are Winchcraft.
So for those of you who don't know, my name is Ryan Scardina.
I'm Colin Licavoli.
I'm Robert Allen.
And I'm Evelina Aksanov. And I'm going to introduce you guys to the challenge that our team faced. So every year, over 8 million square acres burn every year.
And collecting data in these extreme environments is risky and challenging.
Researchers need a safer, smarter, and more efficient solution.
The origin of this product was the Clark 3. As you can see, it had a 3 kilogram capacity. It was relatively fragile because of the PLA filament. It was susceptible to backdriving, and it also had no fire data collection equipment. So we, in our first step of the design, was to figure out where do we go from here, and how do we make the best possible product for the next iteration. And with that being said, we would like to introduce the Clark 5T.
Clark 5T is a customizable light-duty aerial recovery kit with 5 kilogram payload and a thermopod.
Our team came up with a list of system requirements, with the most important one being that we create a functioning winch. We also challenged ourselves to increase the payload capacity from 3 kilograms to 5 kilograms and be able to spool 20 meters of line. Secondly, we also wanted to develop a data collection system that would be able to withstand the high temperature environments of wildfires, which typically range from 800 to 1200 degrees Celsius. And finally, we wanted to be able to fully winch the payout line, so reel it in and reel it out in the full 20 meters in about 5 minutes in order to minimize damage to the actual winch. So the winch has 4 main components. It has a DC motor, which drives pretty much the whole system. It has a diamond gear level line, which it guides the spool so that we have minimal spooling issues. It has a worm gearbox, which produces high torque, and it also has a 26 gauge nichrome line. So this line will be able to withstand the 1200 degrees Celsius high temperature environments.
The Clark 5T made design improvements in several areas, adding to the overall amount of capabilities that it has. So firstly, it now can support a 5 kilogram payload and can be lowered and raised 20 meters in just under 10 total minutes. Part of the problem with the Clark 3 was backdriving, which is where the payload is forcibly lowered due to the overwhelming amount of weight. With the addition of worm gears into our system, backdriving is essentially impossible, so the chance of failure has been significantly decreased. Additionally, the line is distributed across the spool using a level wind, which mechanically moves through a diamond gear, ensuring even distribution from end to end of the spool. aside from the mechanical features, we researched and updated the material filament for each piece of the entire winch. So for the housing elements, we used polycarbonate filament to increase the strength of the load-bearing elements. For the moving pieces, more active pieces like the driven gears and the diamond gear bit, which are all 3D printed, we use nylon, which has increased slip and decreased friction, which allows for smoother movement. And then for the driving gears, which is the worm gear, and then as well as the shafts, we use metal, which increases the durability and lifespan of the gears and provides more support internally for the structure.
So like I said earlier, the system is driven pretty much by a brushed DC motor. And we also needed a motor controller. So we used an H-bridge in order to introduce bidirectional capabilities. And finally, we're using a Hall effect sensor to be able to measure how fast we are spooling in or out. And we do this by embedding a magnet in the spool. So every time the spool does a full rotation, the Hall effect sensor will pick it up and we can measure how fast it's going based off of that. And in terms of communicating with the drone and the winch, so pretty much the drone has a battery and it also produces a PWM signal. So depending, so the battery powers the motor, and depending on what the PWM signal is, we can get the motor going in either clockwise or counterclockwise, which will then turn the shaft in different directions, spooling up or down, depending on what we want it to do.
Now introducing the thermopod. The thermopod is a capsule that allows us to hold our electronics at an operational temperature while also exposing the exterior of the pod and our temperature sensor to extreme conditions.
The PCB is the brain of the entire thermopod. It has the microcontroller, which is autologger feather. It connects the data from the thermocouple and collects it into the SD card, which can be extractable by the user. And so since the whole goal of the thermopod is to collect the data, all of this electronics has to be protected.
To make our open source thermopod more accessible to a wide variety of users, we decided to prioritize variability. We did this by standardizing the manufacturing process as follows. So we first took our double wall stainless steel water bottle, the cap of it, I'm sorry, and in our case, it was a Yeti Rambler, and made a silicone mold. With that mold, we took plaster of Paris and created a physical cap. Once we had the cap, we drilled a hole through the cap and fed the hollowed out screw through the hole, and were able to attach our lifting eye nut. After that, we took our thermocouples, fed it through the hollowed out screw and sealed it with plaster of Paris, and that also eliminates heat transfer to our electronics.
After performing some of the destructive fire tests, we were able to quantify the internal temperature change of our system. So after 30 seconds of being in a fire pit, which was 30 seconds is our system requirement, the temperature increased by 3 degrees Celsius. After 90, it increased by 11. And when we pushed it to 5 minutes, it increased by over 100. But since 30 seconds was our system requirement, it means that we surpassed it by over 10 times, and our system also survived multiple active flamethrower applications for over 1 minute.
So we expect our product to save consumers a lot of money, considering that a lot of current market options are much more expensive. They could cost thousands of dollars, which could be more than the actual drone.
It also increases safety for infrastructure, property, and environment.
And then finally, it increases preparedness. So there's much improved wildfire response times. Thank you.
I have time for one question.
Jared Hershey. He said, did you consider a brushless motor?
Yeah. So we have two motors, and because the system has to be customizable and versatile, you can actually exchange two motors. You just have to modify a little bit of the voltage intake by the motor, but you can use both, yes.
Just to add on to that, we are using a brushed motor, but that's just because the specs of it are better than the current brushless motor we have. But like Evelina said, you could switch it out if you were to spend more money on a better motor.
It would be easy to swap out too, because you would, instead of using an H bridge with a brushless motor, you would use a ESC or electronic speed controller.
Dr. Crow?
Potentially, Dr. Crow?
Probably not.
Unless you made it insurance of the building.
Boo him. All right, thank you again.
Thank you.
All right, I'd like to invite Type Ship up.
I don't even like
Okay. Word.
Got an angle there.
I'm coming back. I was waiting to start the time.
All right. Hi guys, thanks everybody for being here today. We are Type Ship. I'm Jackson. I'm Soma.
I'm Matheus.
I'm Keith.
I'm Cole. Get into it. So first off, I want to cover why this project is important, and first to understanding that is understanding the harms of fossil fuels in the maritime industry. Currently, the maritime industry accounts for about 3% of global greenhouse gas emissions, which causes pretty significant harm, polluting and disrupting fragile coastline ecosystems, which is what we were focusing on in this project. Not only does this pollute these ecosystems, but these effects can also release heavy metals in the forms of oil and gas spills, which can eventually make its way up the food chain, and then not just harming these ecosystems, but get to the point where it's harming people themselves. So moving on to our solution, the Promoting Electric Propulsion Competition, or PEP. This is hosted by the American Society of Naval Engineers. And in this competition, we were competing against much larger schools and schools that were higher funded, having better access to financial and technical resources that we just didn't have access to here. The goal of this competition was really to inspire change and inspire future generations to pursue routes in renewable energies and in renewable technologies such as this. The goal of this competition really was to compete and finish a 5-mile course in under 45 minutes. But before we could do that, we had to meet several key requirements. The first being that we had a fully electrically powered vehicle. The second is that the system has a system voltage under 55 volts and a capacity under 500 amp hours. And the third being that we adhere to all safety regulations outlined by the U.S. Coast Guard.
Yeah, so getting into the boat breakdown, here you have a picture of our entire hull. In the first part of our boat, the battery storage, we had some signs donated to us by the DOT in North Carolina, which we used to encase our battery storage. Second, here we have the steering system that we use. The previous team had like a tiller arm system where they were like steering backwards while going forward, so we thought of changing that. The third, we have a coolant system up in the top right. It's 70 psi, and it's water cooled for the ME1616 motor, which we're getting into here. It's the fourth item, and this is a brushless liquid cooled motor. And fifth, we have the outboard motor, which is a 1974 35 horsepower gas motor, which we stripped down and converted into an electric motor. And then sixth, we have our SubCon controller, motor controller generator, or motor controller, which we'll just get into.
So our main component is the motor controller. So our motor is the ME1616 brushless AC electric motor. It's a liquid cooled 48 volts, 260 amps, and has a 45 newton meters of torque. That worked pretty well. Our first motor controller was the 1238E Curtis motor controller. However, it had a wrong encoding style and it didn't work with our motor. So we had to change the motor controller. That was a $1,800 mistake for our budget. So the first one, so we got our second motor controller, the SubCon Gen 4 motor controller, works in a range of 36 to 48 volts and a max of 650 amps. And that worked pretty well until the night before the competition. So it had an encoder error and we had to overnight from California. and the new one arrived 2 hours before the race. So, but that worked.
And then next up, we have our power system. So this is just an image of our orientation of our batteries. We had a total of 30 cells giving us 48 voltage or 48 volts. And the total power of the pack was around 12 kilowatts. And the amp hour of the pack was 148 amp hours. Here we just have 16 cells on the left and 14 cells on the right with 2 open connections for 2 negative terminals and 2 positive terminals that just led to the power flow of our boat just going straight to the motor.
So getting into a little bit how we actually mounted all this together, like someone touched on, the last team used a tiller system, which was pretty inefficient and was actually very difficult to operate. So we took this outboard engine, completely stripped the gas unit, but then we had to figure out how to mount the ME1616 to it and how to transfer power down the shaft. So we made this CAD model and had that cut by a send cut send. And then after some final machining in-house, we welded it all together. Then our next challenge was transferring the power. Now we made this L-jaw coupling, but it had a weird spline gear in that outboard assembly. And we had to cut off the crankshaft, which was originally mated to it, and machined it down into fit into that coupling to actually transfer the power down the shaft.
As the team was discussing earlier, the steering system last year wasn't the most efficient, so we wanted to improve on that as much as we could. So we designed and built our own steering housing that was bracketed into the 2 benches within the hull. There's 2 angle bars that were welded by our own Barry Keithsill, welded together to other steel plates as well, and then bolted into the bench, where that held the rotary steering kit that we were able to purchase from Amazon. Came pretty quickly and easy to apply. And that was very stationary. That's what kept it that way. But we also had to make some innovations to the back end for the outboard of the hull as well, because there was no place to insert the steering system. There was just like a support rod. It's a little bit hard to see in the photo, but we had to buy a replacement tilt tube to go inside of the outboard there that hold the actual steering cable as you inserted it. So as you insert that through there, connected a connecting arm then to the outboard of the housing that was able to rotate as you then turn the steering wheel, which allowed us to have a little bit more control over the steering that we had and a little more trustworthy instead of, again, having to drive backwards like last year's team. So very efficient, and we're very happy we made that innovation.
So after we got everything assembled and connected to the boat, we did 3 rounds of testing in Salem Lake and in Bellows Lake. First round was amazing, handled like a dream, super fun. Went back the next day, and it was great for about 15 minutes. And then the controller threw an error. We couldn't get it fixed that day, but about 3 days later, we did get it running again and went to our final round of testing in Salem Lake, which was the day before we were supposed to leave for Virginia Beach. That's where we achieved a top speed of 18 miles an hour in calm conditions, and we were ready to put the boat on the trailer and drive to Virginia Beach for the competition. We did the qualifying round, and that was good until we tried to put the boat on the trailer when the controller broke again. So we spent the rest of that day trying to fix it, and even though we did find some wiring misconnections inside the motor, that didn't fix our error, and that led us to getting a new controller shipped overnight.
So then finally coming to race day. So yeah, the controller shipped overnight and it came in at 10 a.m. We raced at 1 p.m. So we were on a little bit of a tight timeline to say the very least. But once we actually had it functioning and operating, we were able to push it into the water and it operated beautifully. We only operated at about 75% power during the race itself because we didn't want to risk any issues with the motor because obviously we're having some iffiness here or there. So we operated about 12 miles an hour and we finished 5 miles in about 25 or so minutes. Around the other planning holes, we placed second place against another 15 or so teams that raced within that competition, beating reigning champion Princeton, which has aggressive amounts of funding for their boat. Thank you. So yeah, the second place prize was $2,000 that we were able to put back towards the little bit over budget spending that we had for that motor controller. So that was very appreciated, especially for the engineering department as well. Obviously, this was a aggressively complicated project. We've had a fantastic time going with it, but obviously we could not have done this ourselves. So there's plenty of thank yous that we have to give to everybody. Joel, the parking lot guy, for allowing us to charge our batteries beforehand. Dr. Briscoe, who was running the event itself. The DOT, Department of Transportation, for donating us signs to use for our battery box. Obviously, Professor Crow for all the wisdom he's given us. And then Mr. Mulder and Nick Golden as well for all the assistance when it came to actually machining some of the components of the whole. So thank you guys so much. It would not have been possible without you guys. Thank you, everybody. Type shit.
We got no time for questions. You guys went over budget and overtime. Next, I'd like to welcome Truck Techs up here. We have this one, and then we have another one. So either one you like, or you can just click on that. There you go.
Hello, everyone. We are the Truck Techs. I'm Lorena. This is Jesse, Kirk, Ben, and Tucker. And we are the Truck Techs, sorry. And this is our Capstone project.
So power outages across America are becoming longer lasting and more frequent. According to the U.S. Census Bureau, the average U.S. power outage has doubled from 3.5 hours to 7 hours between 2013 and 2021, with extreme weather being the leading cause. This can have major effects, especially to vulnerable communities. For example, in 2023, around 14.5 million households reported having medical devices that required electricity to operate at. Nearly a third of these households were affected by power outages. So to address some of the power outage issues, we partnered with Alltech's Mount Airy campus to try to come up with a solution to try to respond to these power outages faster.
The problem is that Alltech's current rope winding process for their puller tensioner truck is manual and inefficient. Operators always have to constantly adjust the brake as the spool diameter decreases, which leads to inconsistencies in rope tension and frequent delays. Also, another complication is that there is no method to measure tension, which opposes safeties, and yes.
Yeah. All right, so this is our system requirements. So our main requirement here is to have a target tension of around 10% of the rope's max capacity. So this is kind of an industry standard. And Alltech gave us a 50 pound plus or minus tolerance. So we don't need to be right on the dot, but within reason. Our solution has to be transportable by a forklift, work with different sorts of ropes of different densities and different diameters and whatnot. Also, we need to meet the OSHA and NEC regulations for safety. And lastly, have an external user interface in order to set the parameters of each individual roll as they begin unloading it.
So this is an overview of our prototype right now, and I'll get into kind of more of the components on the next slide. So first and foremost, our prototype does not actually drive the spool. That's done by a motorized drum on the truck, which we have simulated with this half of our model. On the other side, we have two inputs to our microcontroller, which is the brain of our system. We have a digital encoder, which is reading the number of times our spool spins. And then we have a pressure sensor, which is connected to our braking system. So our whole system is resisting the motion of this motorized drum, which will create the tension in the line. The encoder and the pressure sensor send their information over to the Arduino microcontroller. That does a bunch of math, calculate what the tension is, and compare it to what our target is. And then a stepper motor will drive our braking system, which will either increase or decrease the pressure in the brake and allow more or less motion.
Okay, so all this is well and good. A lot of electrical components, but they need power, right? So we've been collaborating a lot with Alltech, the operators on the Alltech production floor. And we realized they need to be moving this loading system all the time, so we can't use outlets on the floor because you never know when they're loading. So we need a way to power this thing mobily. But we also know that operators love their Milwaukee batteries. For whatever reason, they just love them. So we said, all right, we'll power the whole thing off Milwaukee battery. So we did that. That means we have to step the voltage up to 24 volts when powering the actual stepper motor. as well as pressure transducer, and step it down to power the Arduino Mega and the encoder. So this is, we collaborated with Altec, and they actually machined us an entire steel prototype, which is awesome. So we got this spool here simulates the pulling tension of your truck. So this will be pulling against our system here, which will be resisting it, creating the tension in the line here. So this motor spins. We adjust the brake on this part using the stepper. We drive the screw in. It compresses the brake, similar to any brake on a car, right? And that tension there is created. Next slide. So given our system requirements, it works. We were able to drive the motor. We were able to read the tension, drive the motor to the correct distance in the screw, and create the tension within our given limits by Altec. It meets all OSHA and NEC standards. It's compatible with any rope size they use. They change rope sizes a lot. We just have to change the inputs. But we were unable to make the UI that user-friendly, so we'll have to train Altec.
We're expecting our system to have many societal impacts. On the social side, we're hoping that this enhances safety and efficiency during power outage relief and reduces manual labor, since this eliminates the operator turning in and manually adjusting the brake. On the environmental side, we are hoping that this minimizes waste and energy consumption by using a rechargeable battery, and it enables quicker power outage relief to lessen effects to the environment. On the economic side, this increases productivity and minimizes labor costs by reducing the manual labor. And we're hoping this speeds up recovering during power outages, which power outages can be very, very expensive for communities, and hopefully get some product for Altec.
So in the future, we want to deliver our prototype to Altec and kind of give them the documentation and sort of instructions on how to use it. We also, right now, we just have it implemented on a small scale prototype. So we would like to implement on a full size A-frame that they actually use at the Altec facility. We also still need to get working on that UI in the future, just so that they can update parameters depending on different spool sizes and different rope characteristics. And then lastly, we want to upgrade our microcontroller. We have an Arduino Mega, and we figured that it might be better to get a more robust microcontroller meant for actual industry applications.
Thank you.
Fortunately, stay on time. Let's keep rolling. All right, last but certainly not least is mission decondition.
Good afternoon. We are Mission Decondition, and our goal is to redefine mobility and restore strength.
I'm Miguel Burgos.
I'm Haley Denton.
I'm Robbie Graham.
I'm Ava Honorado.
And I'm Ethan Rodriguez.
So what is deconditioning? Deconditioning is the decrease in muscle mass caused by prolonged bed rest or inactivity, and this can lead to health complications, including muscle atrophy or the breakdown of muscle tissue, a lack of circulation in the bloodstream due to immobility, and this can accelerate muscle degradation and lead to an increased risk of blood clots, as well as the lack of mechanical stresses on the bones can lead to a decrease in bone density, and this causes patients to become more prone to fractures.
So 30 to 50% of ICU patients are affected by deconditioning, and this happens at a rate of about 2% per day. So over the course of 10 days stay in the ICU, you can lose up to 20% of your muscle mass. And we have committed ourselves to preventing deconditioning and those longer times in the ICU by creating a novel bed bike for use in the Atrium Health ICU to avoid these negative physical consequences. This also comes with negative social and economic consequences. So to avoid those problems, our broader impact goals include a decreased patient medical bill and a saving money for hospitals because it costs thousands of dollars per day to stay in the ICU. Socially, shorter hospital stays are obviously associated with improved mental and physical health, and to avoid post-discharge rehab, that will also improve mental and physical outcomes. Environmentally, we make sure to use reusable, recyclable, and eco-friendly materials to improve sustainability and limit manufacturing emissions.
So onto our mission, to address our problems, we have a lot of these methods. We've been working to build an affordable exercise apparatus that is safe, easy to use, and most importantly, effectively activates the muscles of the legs through active and passive motion. This way we can get patients out of their beds as fast as possible.
So that has led us to come up with 5 overall system requirements to optimize both the patient and the hospital staff experience when working with this device. So the first one is that it's functional. We wanted to our product engages the correct leg muscles as verified through electromyography testing. It also has patient-controlled motor speed as well as variable resistance, and as well as gives live feedback in the form of a touchscreen user interface. Our next one is that it's compatible. We wanted to make sure that it fits on the Stryker bed so that it is makes for easy sliding in and out, as well as fulfills regulatory codes and standards. And then the third one is that it is adjustable to cater to all patients' sizes and ages. And so we wanted to have various heights, calf circumferences, as well as overall movement.
Safety is critical in an ICU setting, so to ensure that our device is safe, we put in an emergency stop switch on the remote so that the patient is able to access it at any time throughout their workout, along with the stability feature to prevent any erratic movement of the lower limbs for patients with less control. Finally, we wanted this to be easy to implement because hospital staff is already busy as is in their day-to-day. We wanted to ensure that our device took only 3 minutes to set up. It was easily transportable from room to room, and it was affordable for healthcare systems to acquire.
So that brings us to our solution. Centered here is our 3D model, and starting from left to right, I'm going to go over the specific components. So starting on the left, we have our compatible footboard with those insertion poles that you can kind of see on the bottom. Those will go into the footboard of the Stryker bed once you take out the existing footboard of the bed. And then screwed into the back of the footboard is the electrical system that houses all of the electrical components, which Robbie will get into later. And then at the top, you can see that touchscreen user interface that when someone is pedaling, it displays heart rate, cadence, and power output of the bed bike. Switching to the other side of the footboard, we have our height adjustability feature, which due to its telescoping tube feature can cater to those various leg lengths that I talked about earlier. Then moving to the middle, we have our PLA casing, which houses our brushless DC motor, which facilitates both passive and active motion. Passive motion is when your legs are strapped in and the bed bike is doing the pedaling for you, whereas active motion is when you are pedaling yourself with that variable resistance. And then as you look towards the extremities, you can see the lower limb stability cuffs. That is for calf support and ensures patient safety and prevents injury.
Cool. So after planning and designing, we want to manufacture it. Everybody on the team kind of specializes in one feature of our product and work tirelessly to bring it to life. So the first thing I want to talk about is Stryker bed compatibility. This is a really important concept for our project because we make sure that our project is compatible with the we have made our product to be easily installed and seconds so that nurses can set it and forget it. Moving on to the motor, like people said, we have active and passive motion. This has multiple speeds that multi-resistance, the active and passive motion can be adjusted through a dial, and also have the emergency save and talk about all patients. And as far as the workout feedback screen, it shows your cadence, your heart rate, and then your power as well as the past workouts that the patient kind of keep track as a patient we have going up in the system. And then you have also the dual axis adjustability that makes sure that our system fits for all heights and sizes as well. It's also adjusted. And then lastly, we have a leg brace for all the pedaling.
All right, there's a lot going on mechanically and electrically behind Typically, the system operates in two modes. So when it switches off, the dynamic range can be here as the user tells. The motor generates electricity, and this current creates an electromagnetic resistance felt by the user. So current here, in this case, is represented by the red arrows in the diagram. The offset is used to regulate this current to allow control variable. Then when the switch is turned on a set of relays disconnect the registers, and the motor draws current into the line. The resistance level and motor speed are controlled by the Arduino based on the same counter input. Also, a Raspberry Pi is utilized to run the direct application. Then sensor to calculate the PNP power output, while simultaneously.
So join us in redefining rehab in the ICU. By using our bedbag apparatus on a regimen provided by a healthcare professional, patients can combat deconditioning before atrophy begins. And this would mean improved and faster recovery for ICU patients, a decreased length of in-hospital stays, and patients may be discharged straight home with minimal hospital intervention, saving patients and hospitals money.
Thank you. Questions? I think we have no time for questions as well, but I would invite all of you to come to our showcase on Monday, where you can chat with all of our teams. Let me close this up really quick here. All right. All right. So that was awesome. What an awesome display of innovation, dedication, and problem solving. I know I've seen all of your projects individually, but it's really inspiring to see all of them kind of put together like this. And I'm sure all the rest of our visiting folks agree, and their faculty and staff. I know that this is, we're all kind of eager to go, so I'll keep it kind of short here. But I know that this Capstone Showcase is kind of more than just the presentations, right? It's your all's kind of bridge between your academic learning that you've done here at Wake Forest and the practical applications that you have applied to these real world challenges. So seeing these projects come to life is always a highlight of the academic year, and it reminds us of the power of the engineering design thinking, particularly when nurtured within the broad perspective of the liberal arts environment here at Wake Forest. I want to extend a real thank you to everyone who came out to support our students here, including the engineering faculty and staff. Thank you all for your guidance and mentorship throughout the last few years for our students. Thank you to our technical mentors, many of you are here today, for your real world experience and practical advice that have been absolutely critical to finishing these projects. Any families and friends we have here in person or watching online, thank you for supporting and encouraging all of our students. I know that that's kind of their foundation here. And to the many members of the local community who have visited us here today. That kind of validates the long hours and hard work that our students have had on these projects. So before we actually conclude, I want to get everyone here's input. So this is the People's Choice Award. And I would like for everyone to quickly take out your phones and scan this QR code so you can vote for the People's Choice. This is your opportunity to see which presentation here today resonated best with who is here. I'll give everybody just a few seconds to scan this and go ahead and do a little voting. Everyone online, I encourage you to do the same with your computer screen. We did earlier. So while you're voting, this People's Choice Award is one of 4 honors that we will present to Capstone teams. The other awards will recognize outstanding prototyping, commitment to the pro humanitate values in design,
and overall excellence in the design process. That one's the Coach's Choice Award, and in my opinion, the most coveted award, mostly because Dr. DiVittorio and I award that one. We choose and award that one. And we'll announce all 4 awards at the conclusion of our showcase on Monday. Please vote now, and then we'll announce those on Monday. So lastly, this is my kind of opportunity in front of all of you to thank all of the senior students. I just want you to take a moment to reflect on what you've accomplished here. You kind of saw this culmination here today, and I know that this year has demanded perseverance, some late nights probably, intense collaboration, and moments where the path forward was not clear, to say the least. You navigated all of that. The projects that we saw today are not just technical exercises, but they're testaments to your growth, your ingenuity, your resilience, and your ability to work together to create something meaningful. We, the faculty and staff of the engineering department, are so proud of each and every one of you. Thank you for your dedication, curiosity, hard work, and for making this such a rewarding year. It's been such an honor to work with all of you, and I know that you guys are ready for this next chapter. At least I can't wait to see the impact that you all are going to make. I'm really proud of you guys. Thank you all for joining us to celebrate the outstanding achievements of these students here today. On Monday, we have a bit of a celebration of all of our students, starting with the freshman cardboard showcase. I encourage you all to come to that from 9 to 10 a.m. Following that, we have the Capstone showcase from 11:30 to 1, and then another cardboard showcase shortly after that. If you could come to our Capstone showcase, you can ask those questions that you might have had today but didn't have the time to ask, interact with prototypes, and chat more with our students. And at the conclusion of that, we will announce the winners of our 4 Capstone Awards, and you won't want to miss that. I hope you have a wonderful day, and I hope to see you all on Monday. Thank you so much. Really quick, all the students, if you guys have a moment, we're going to meet outside and take a quick class photo. Outside, unless it's raining. I don't think it is, though.